we'll get you sorted out. All right. Okay, let's get ready to go then. So welcome everybody to our 13th meetup. So we lasted a year or 1 month. And thank you to Yammer to hosting us. They're going to have a little message. And the next meetup is happening in April, and it's going to be on logical time. And our speaker is over there, Jordan. So if you have any questions, that will be his talk. So let's get ready to start. And yeah, go ahead.
Hi, I'm Clark. I work in infrastructure here at Yammer. Welcome to our office. We're glad to have you here. Thanks to Inez for giving us the opportunity to host, and briefly mention that we are hiring. Won't bore you. If you are interested at all with what we're doing and what Yammer is, find me or Micken after the talk, and we'll be happy to talk with you. Thanks.
All right. So give it up for Matt. And Matt is going to do our first mini. Talking about minis, we are covered until August. So if you have an idea or if you have a paper and you want to present 10 to 15 minutes of it, ping me on the Twitters and I will get you in the books. So give it to Matt.
Cool. Thank you. Hi, everyone. I'm Matt Adereth, and I'm going to be giving a mini talk on the mode tree. It's by these two statisticians, Minot and Scott, and it's from 1993. All right. So the problem starts when we start making some observations of something. It could be ages of people in the room. It could be the time that some benchmark took to run. But we get a bunch of numbers, and we want to understand the shape of the distribution that these come from. So there are a bunch of things that we can do. We can compute the mean and the min and the max and the standard deviation and try to get a feel for the shape of the distribution from that. But that doesn't really tell us everything. So there are other more esoteric things that we could use to try and describe this with numbers. There's the kurtosis and skew, but that doesn't mean anything to humans. So what we all do is we plot it. Right, so we make a histogram. That's the most common visualization. So let's make a histogram of this data here. All right, here's the shittiest possible histogram that you can make. So I've used a bucket size of 30, and it tells us nothing. We get the count. Great. So the problem is that our bucket size was too big. So what if we use a smaller bucket size? So here we're using a bucket size of 10. And we start to see some shape, right? And it looks like there's a peak in the middle here, and that's what we call a mode. It's where the data is the densest. Now, an interesting thing with the histogram here with a bucket size 10 is that it's very sensitive to where we started the buckets, where they're aligned to. So here, it's natural we started them at 0, but what if we had started with the buckets centered at 0? So we would have gotten this histogram, and that looks different. So it's kind of troubling. But smaller buckets are better. So let's look at if we use bucket size 2. Now I know the data set that this was sampled from, and I know that this looks really good. We've got this one bump over here, and then this bigger bump over here that maybe is made up of 2 bumps, and we can see that. So. Smaller bucket size is better, so let's make it even smaller. And then we get to what's arguably the second shittiest histogram for this data, where each bucket just contains a single value. There is actually an optimal bucket size that one of the authors of this paper, David Scott, came up with in 1978, where if you believe that your data is normally distributed, the optimal bucket size is 3.5 times the standard deviation over the cube root of n. That's cool. Important histogram theory. But that assumes that it's from a single normal distribution, which it may not be. So we saw different things appear at different bucket widths. Wouldn't it be cool if we could see every bucket width at once? And that's what the mode tree tries to give us. So the way that we make the mode tree is we actually use something a little more sophisticated than a histogram. We use what's called a kernel density estimate. So here's the formula for the kernel density estimate, and we'll just take this apart. So what we do is we pick what's called a kernel function, k. And this could be anything, but the right thing is to use a normal distribution, and they get to y in the paper. So we pick like a normal Gaussian distribution, and we make n copies of it, one for each point, and we center it at each point. And then we have this scaling factor that lets us make it wider and if we want. In the case of the normal distribution, this h ends up being exactly what the standard deviation of that distribution is. And then we just sum it up. We make a copy for each one, and we just add it up, and we get a continuous fancy histogram. It's an estimate of the probability density function, if that means anything to you. But we get something that tells us where the data is. Now, it's better than a histogram for a couple of reasons. One is it's not sensitive to the starting point like we saw the histogram was. Like, we only have one dimension that we can tune, the h, which is like analogous to the bucket width. Also, it gives us very precise values for the max, for the modes, like where we think the data is concentrated. Whereas with the histogram, we would see that there was a bar that was the tallest, but like the true mode could be anywhere along that value. Here we get a specific number. So we can look at different h values, just like we looked at different bucket widths. We can use a bigger h and get a smoother estimate for it. Here we just see there are 2 mounds. We can use a smaller h and get something that's a little more spiky, that shows us more of the details. But we kind of think that some of these are just like artifacts of noise in our sample. So we have this kernel density estimate, and now we can look at it for every for like a bunch of different kernel widths at once. So let's do that. And they talk about this in the paper. Like, they show this visualization of like overlaying a bunch of kernel density estimates. That worked. Cool. And you get this one view into into a bunch of different widths, and different details of the data are all apparent to you at once. But they call out a bunch of reasons why this isn't great. It kind of overemphasizes the spikes at the smaller widths. And it also, like, your eye gets drawn to these downward bumps. These are called the anti-modes. It's where the data isn't. So that's not so great. So then they came up, they were like, all right, this is too much. And then there's like this whole 3D one, which is garbage. And they came up with the mode tree. So now let's look at the titular visualization. So the way that you make the mode tree is you start with a really big kernel width, and you get your kernel density estimate, and you pick one that's so wide that you only have a single peak. And you find that peak, and we're gonna watch where the peak moves as we shrink the width. And we're gonna plot it down here on the mode tree. So the x-axis here is the same x-axis as our data, and the y-axis is the kernel width. And they recommend using a logarithmic scale because it's better. So let's look at what happens as we shrink the width, and we just trace out where the mode moves, and then a wild mode appears over here, and we plot where that is, and we connect them up with a dotted line, and then we just keep going. We keep shrinking the kernel and following the bumps, and then a third appears. Now, when the third one appears, it's not obvious which one you should connect it to. Like, we could connect it to this one or connect it to that one. And we pick the mode that was the top of the bump that point was in on the previous value of h. So each mode has a parent. Each mode has one parent, and each bump splits into two eventually. And then we just keep going. And eventually we stop. if you were to take this all the way, you would eventually end up with it split so that there was a line for every point in our data set. So this is the mode tree. Maybe somebody knows how, maybe like if you look at 100 of them, you get an intuition for what they mean. I haven't done that yet. But what they do in the paper is look at different things that you can layer on top of this to get even more insight into the data. And the big thing that they do is the most important addition is that they add little circles to each of the forks, and then they do a statistical test on that value to determine whether or not it's significant, whether or not we think that bump is a true feature of the underlying data set. And it's really cool because it's not, it allows you to detect like narrow bumps that are close together. So like in the case, like the scenario that I always have in my mind when I'm thinking about this is I'm thinking about it in the context of benchmarks. Like what if sometimes my function is like entirely in the L1 cache, and sometimes it goes to L2, and sometimes it like goes to the network. Like, is there any way to detect like those three different modes when those two cache timings are going to be so close to each other? So then they go nuts, and they do a bunch of other things that I'll just show you, like putting additional things to show you, like the dotted lines here are the anti-modes, and the gray areas are like the widths of the bumps, and good luck. This is a different data set, just in case anybody was trying to map it back to the previous one. This is from the paper. And then they look at it in for multivariate distributions, and good luck. It's cool though. And then a few years later, they had this really cool paper called The Bumpy Road to the Mode Forest. They refer to themselves as bump hunters. That's a statistician thing. So what they do here is at each width, they do random sampling of the points and look at where the mode is, and they keep doing that a bunch, and then they get these like clouds of where the mode might be, and this is more robust against noise, and it's prettier. It's a mode forest. So that's it. That's the mode tree. I hope I've conveyed my love for this paper. I don't know if it's actually like useful on its own, but it is. The thing that I really love about it is that it is a view into how some of these kind of difficult to approach algorithms work. And I really like that these researchers kind of took this distraction of writing up a paper about a visualization tool that they came up with to help them think of the algorithm. And I thought that was cool. So if anybody has any questions, I don't know if we have time, but I'll be at the bar, so you can geek out. Okay, cool. The question was, what did I use to visualize it? This is just like a massive D3 callback hell. Yeah, write once, present once, never look at the code again. Yeah.
So that last mode forest, the one that looked a bit like a smoky heat map. What determined how wide the smoke was, how dark it was, all of that? It looked like there was some information being presented that I wasn't quite able to parse.
So I do not have back technology in my ad hoc presentation framework that I wrote for this. So I think what they did was at each, they would do some random sampling of the points and look for the mode, and then like throw down a point at like a pixel there with some alpha that they selected, whatever ended up being pretty. Yeah. So I don't think anybody did, besides the authors of this paper who then did the bumpy road to the mode forest. I don't think anybody else has looked at the doing more with the visualizations. There's a lot more work with mode detection algorithms. That's super interesting and is why I got distracted by it. That's what I was actually supposed to be looking at when I got distracted by this. But I do think that there is something there. I think that the mode tree isn't great on its own. You have to know what a kernel density estimate is. It requires a little too much background. It's not as approachable as maybe a box plot. But I'm not convinced that a box plot is actually approachable. It's just that we've seen so many of them, we get used to it. I would like maybe myself or somebody else to come up with some simplified, accessible versions. What's the box plot that shows you multimodality? I think that would be an interesting direction to take with it.
What were those data points that you were using?
The question was, well, you heard. The data points that I was using just for the demo it was just a Gaussian mixture. There were 3 Gaussian distributions. 2 of them had probability 1/4 of being selected, and one of them had probability 1/2. And it was just synthetic data that I made up. Maybe one more? All right.
So there's a question that I had when I read the paper, and it was really interesting to see her talk in the context of this. There's this really cool aside, a third of the way in. They're like, it's 1993. And you know what statistical visualizations really need to do? They need to work on paper and transparencies, because nobody has interactive screens at their fingertips all the time. Who has that? Any thoughts on the context of these sort of visualizations today? I've been reading a lot of Brett Victor stuff recently. So how can we make these things explorable? I really enjoyed the animations that you showed, and I thought that gave sort of an intuitive sense if you could scrub back and forth and use that as a method for exploration. So any thought on visualizations like the mode tree in the context of explorable, looking at it on a computer?
No, I think that's a good idea. Yeah, and there are a number of people who were explicitly inspired by Brett Victor and made kernel density estimate visualizations where there's a slider for the width. That's the hello world of trying to be Brett Victor, I guess. But yeah, I think there's a lot of room there. I did think that was an interesting note in there. And one of the things that's kind of cool about all this computational statistics stuff is that they really were limited by the power of their machines at the time. And you could, as you go through the papers, you see them do more and more sophisticated things just because they had more and more computational power. And it's a interesting thing to keep in mind when looking at the papers before and after this. Cool. All right. Thanks, everybody.
So we have a few minutes until Armon gets ready for his talk. So if you want more drinks, All right. We're getting ready to start again. So everybody, I don't know who was here last year or who saw Armon's presentation of last year? Hands? Oh, nice. All right. So this is a cameo. So Armon liked it so much that he decided to do another one, and he's going to be talking today about HyperLogLog and Bloom filters. So an applause for Armon from HashiCorp. Yes.
Thanks to Inez and Yammer for having all of us here. So today we're going to talk about Bloom filters and HyperLogLogs, or the alternative title for this, cutting corners for fun and profit. So for those of you who don't know me, my name is Armon Dadgar. I'm everywhere on the internet as just @Armon. I currently work at HashiCorp. You may have heard of us or some of our tools. We do kind of DevOps, data center automation stuff. Probably heard of Vagrant. So that's our project. But in a past life, I used to work at a mobile advertising company. So the company was called Keep, and the specific details not super important, but the kind of interesting part of an ad network is a few different things. On one, you're talking about an enormous amount of scale. On the other side of it, you have very tight SLAs, where every single millisecond you can measure the drop-offs and conversion, and everything has to be done in real time, right? So everything you can't afford to be like, oh, well, the ad impression came in, let me run a Hadoop job and figure out what I'm going to show you in 8 hours. So a very constrained problem space forces you into some creative thinking. So a few of the problems that we'll talk about, which will kind of provide the inspiration for some of these algorithms we're going to talk about, is one is kind of duplicate impressions. So you can imagine, a request comes in that says, hey, I need an ad to display. You have 20 milliseconds to pick an ad, and you want to make sure that whatever ad you're showing the user, you haven't shown them once, twice, 50 times before. The other few things you might care about is how many unique users do I have on a daily, weekly, monthly basis? And then breaking that down, maybe you care about these metrics on a per application, per country, per software version. And once you start caring about these other kind of axes, you have a combinatorial explosion. So let's tighten this definition a little bit. What you're getting in is basically a stream of these tuples. So you get a user ID, an application, a country, maybe a version, and you care about your combinatorial uniques across this matrix. And what you have to generate on the other side is a stream of user ad impressions, where you want to minimize the amount of duplication that's happening here. So this is kind of the tighter definition of our problem. And so now if we kind of want to think through, okay, what are the possible solutions that we have in this space? Well, one way of thinking about this problem is kind of framing it as a set problem. So let's take an abstract set S. And we have a very simple set. It supports 3 operations. We can add an item to the set. We can check, does this set contain an item? And we can ask for the size or cardinality of the set. And then you can get fancier and support union, intersect, diff, subset, remove. But for our purpose, our very simple set needs 3 methods. And so there's many ways you could go about implementing this, right? One way is insert everything into a database and then run a distinct query, and the database will generate a B tree underneath. And, it's going to do some disk and memory shuffling for you, but, it'll simulate being a set. Let's back up a little bit. So how would we actually use sets to solve this problem? Well, the duplication problem is actually really simple now. We basically have some named set. We're going to call it scene ads. Before we show it to the user, we check, hey, has this user ad tuple been done before? And after we show that impression, we basically set it in the set so that we avoid duplication the next time around. And then for our combinatorial uniques, we basically create a specific set for each interval we care about, each country and each application. And then we just add the user to it every time we see them. So then at the end of the interval, we can check, okay, how many daily United States Angry Birds users were there. The problem with doing this is that there's this multiplicative factor that's taking place. So imagine you have 3 intervals, 100 countries, 1,000 applications. Very quickly, you're talking about millions of sets. So now we get to the question of, okay, well, how do we implement these sets? So one answer is, okay, throw it in a database. It's the database's problem. It's going to build a B tree. You're very quickly going to have a bad time with that approach. If you're talking to disk in general, you're not going to make your 10 millisecond SLA. So it has to be in memory. So the most common implementation is a hash table implementation of a set. So we take our key foo, we run it through some hash function, we mod it by the number of buckets we have. In this case, we end up with 5. We go to the 5th index, we set foo in there. And the great news is the properties of adds, contains, and size, they're all O of 1, constant time. Great, we can do this, 10 milliseconds is no problem. But then the question becomes, well, what is the memory cost of this approach? So let's just say, we're on a 64-bit machine. Each pointer is 8 bytes wide. Each entry we're going to store is 64 bytes. This is just kind of a conservative estimate. It depends on however big your item is. Foo is much smaller than 64. We'll pick a fill factor of 75%. And basically, you can compute out that if we wanted space for 10 million entries, our hash table has to be about 750 megs in size. Now remember, we don't have one set to maintain. We actually have about 1 million. So really, we need about 750 terabytes of RAM to hold all of this in memory. So all of a sudden, this seems like we need a lot of hardware to solve this problem. It's kind of unless you have some extreme budgets in your Google or Facebook, 750 terabytes isn't a joke. So the question becomes, can we do better? Can we somehow tune this factor down? So the biggest cost that we had there was the 8 bytes for the pointer, but the 64 bytes for the entry, right? So why did we even need this entry in the first place? Well, we need the entry because our hash might collide. And if we have a hash collision, then we need to do a key equality check to say, oh, is this item actually in the set, or did we just have a hash collision? But what if we say we don't actually care if we have a hash collision, that it's good enough? What if we allow that error to take place? Can we change this implementation? Well, now instead of actually having to have a pointer to an entry that says, this is foo, instead, we just change that to being a single bit that says, oh yeah, there is something at this index. We just skip the pointer, skip the entry, don't store the key. Well, now what does this do to our memory cost? Well, our bucket has gone from 8 bytes wide to a single bit. We no longer store the entry at all. And so if we keep our fill the same, well, now the space required for that same 10 million entries has dropped to 1.6 megabytes. And the total storage we need is only 1.6 terabytes of RAM instead of 750. Now this number is starting to get a little more manageable. Now you can look at 1.6 terabytes and say, with a few beefy machines, we can actually reasonably hold this in memory. But what's the catch here? We must have lost something. Well, now what we're susceptible to is that we're going to add foo, like we did in the last slide, but now we're going to check, is bar contained by this set? And it just so happens the bar hashes to the same index, and whoops, we're going to say bar is contained in our set. Now we have a false positive. So what we'd really like to know now is, okay, given that we've relaxed our constraints enough that we are able to fit this in memory, what exactly is the error we're now taking? How can we quantify the error that we've just added to our system? So, we'll assume that the distribution of our hash function is uniform. This is, in quotes, a good hash function. It's going to distribute evenly over the space. And so if we have n items in m buckets, this is just like Pigeonhole, what is the chance that we're going to have a collision in this situation if we're adding a new item? Well, it's about 25%, because 25% of our buckets are full. So there's some kind of fundamental trade-off taking place here between the amount of space that we're allocating, which is m, and the collision rate, basically. So if I had, m was also 2, and I had 2 items in it, my collision rate's 100%. If I set m to 5 trillion and I have 2 items in it, my collision rate is going to be, essentially 0. So there is some kind of fundamental trade-off here, but the question is, right now it's directly related, but can we get to a different relationship that isn't quite linear? And that brings us to Bloom filters, basically. And so as the title suggests, it's a space-time trade-off in hash coding with allowable error. It sounds awfully applicable to what we're talking about here. And so the basic concept behind a Bloom filter is actually pretty simple. If you read the paper, I think it's like 6 pages. I think the most interesting part of it is that it has 3 citations. It's literally like citation 1, math. You're like, oh, okay. It's like I think it was published in 1970, and it's like clearly before word processing. It looks like a Xerox copy of a Xerox copy, like 50 levels of turtling. Anyways, so the basic concept is that instead of hashing to a single location, what we do is we hash to k locations. So we have k independent hash functions. And so we modify add now. So all add does is for each k, we compute the hash of k mod m, and we set that bit to 1. And then we modify our contains function to run all k hash functions. And it's true if and only if every index is a 1, false otherwise, right? And so now when we're inserting foo on this side, we run it through hash 1 and hash 2, and we set buckets both 3 and 5 to 1. Well, now you can see that in the bar case, originally when we had one hash function, we were susceptible to that, single collision. Now hash 1 goes to 5, but hash 2 goes to 0. We've avoided the collision, right? And so I don't think that paper talked about it that much, but there's some other work that kind of quantifies and tightens up what is the probability of a collision given this model. And it simplifies down to, I unfortunately didn't use the same math software as him, so mine is much more jank formatted. But you kind of get this effect where the probability of collision in here, in the innermost grouping is less than 1, and now we're raising it to some positive power. And so what you're doing when you're doing that is basically, with each hash function, we're dramatically reducing that collision probability, basically, right? So 0.5 times 0.5, we get to 0.25, times it again by 0.5, 0.125, so on and so forth. So in this very simple case with n, m, and k, basically the hash collision probability here is now only 5% instead of 25% in the simple hash table example. But now we have all these tuning parameters, which is like, how are we supposed to know what to set all of these things to? So you have n, which is the number of items that are going to be set in it, m, which is your storage size, k, your hash functions. There seems to be some kind of trade-off between speed and error here. P, which is our probability of false positives. I screwed that one up. And so there's a few, the papers kind of unpack that, okay, given that we know m and n, we can actually compute the ideal k. So we can minimize the false probability rate given that m and n are given to us. And that's given by basically m over n times log of 2. And then equivalently, we can rotate that around and say, okay, well, if we want to specify our false positivity rate ahead of time, we can compute how much storage should be used. So it's kind of one of these situations where given any two things, we can compute the third thing. So typically, within a problem domain, you're going to know what your n is, and the problem space will tell you, okay, we can tolerate a 1% error or 10% error, and then you can forward compute the other tuning parameters. But with k, the paper specifically says there's a space-time trade-off here, right? And what is that time trade-off we're making? Well, each one of these k hash functions requires us to scan over the input key again and compute a new hash value, right? So for every additional k, we're spending extra CPU time doing more hash functions. On top of that, we need more unique hash functions and unique seeds for them. Some of this problem seems like, it was probably more pressing in 1970 when you were watching the vacuum tube flicker. Now your hash function probably not so important. But nonetheless, there's some math that comes to our rescue, which is this paper that was linked very briefly called Less Hashing, Same Performance. And the basic idea is that we actually only need two hash functions. We need an H1 and an H2. And as long as those two are independent, there's a bunch of math that shows us that we can actually just linearly combine these two to generate the k hash functions. So realistically, we actually only have to do two expensive in air quotes hash functions, and then the rest of it is just an add and multiply, basically, which is, it's free on modern hardware. So, okay, so given that we know p and n ahead of time, we can compute m and k. P depends on our problem domain. But now there's this question of, okay, well, how do you select n, right? And this is, you probably run into this all the time as you're coding. You're like, well, should I, initialize my list to size, 1 or size million, right? It's hard to know in advance. And so most data structures we use are, resizable. They're not so restrictive that, you have to specify in advance what the n is going to be. You pick some reasonable default, it scales and deals with you. The Bloom filter, unfortunately, doesn't quite let us do that. And so if our n is too small, then we'll exhaust our filter. Basically, we've designed it for a very particular n. When we hit that n, we can't allow any further writes to it, because otherwise our error rate just explodes. If we select an n that's too large, then it's very sparse and we've wasted a lot of memory. So how can we kind of intelligently select this n or get around this problem? So with a typical hash table, you set your fill percentage target, And the moment you hit that, you basically resize the table. So it doesn't really affect our runtime because it's still amortized constant time. The key here is you require the keys to actually rehash. So if I double the size of my table, I have to run every key through the hash function again. But now I'm instead of doing hash of x mod m, I'm doing hash of x mod c of m, where I've multiplied by 2 or by 4 or whatever. The problem is these two are not necessarily equal, right? And so in the Bloom filter's case, we know in some sense what hash of x mod m is, but we don't have x anymore. So we can't run it through the second hash function and figure out what the new index would be. There's no sane resize, right? It's gone through a hash function. It's not reversible. And so that brings us to scalable Bloom filters, the third paper on the Bloom filter list. So the idea behind it is actually pretty simple. So we pick a target p, false positivity rate p, and then we pick an initial n. The initial n doesn't have to be our final size. And what we do is when we've exhausted a Bloom filter, we just create a new one that's a larger size. And then we actually just layer each filter one on top of the next. And so this modifies the add and contains operation in a pretty simple way. All that happens to add is now we always hash the key and insert into the largest filter. So kind of the topmost filter is the one we're appending to. And anytime we're doing a check, we scan every level, basically, for a hit. And so in this case, maybe we've inserted foo previously. We check the highest most entry. Oh, looks like it's not at index 4. We check it again at layer 1. It is in layer 1. Okay, this filter, the scalable Bloom filter, contains foo. But this now introduces a few new tuning parameters that we didn't have before, which is now, okay, now we have this S factor, which is, do we double it? Do we triple it? Do we 10x it every time? How are we supposed to pick that? And basically what the paper unpacks for us is that if we set this S value too small, so basically I take my filter and now I make a new one that's only 10% larger than it the next time around, well, if your growth rate is high, you're going to end up with many, many layers, right? If each one is only 10% larger, maybe I need 100 layers to accommodate a doubling in growth. And now I'm going to waste an immense amount of CPU time. Every time I do a contains operation, I have to scan 100 levels of Bloom filters. If I go too large, then once again, I'm going to have a very sparse Bloom filter, and I'm going to waste a whole bunch of memory. So if I just 10x every time, very quickly I'm going to have, Bloom filters that are in the multi-gigabyte range. And so what they show is basically S should pretty much just be hard-coded to 2 or 4. If your data is slow growing, you set it to 2. If it's fast growing, you set it to 4. And then you just kind of hand wave. That's kind of the conclusion of S. But then there's this more subtle parameter R. And R is an interesting one. So the kind of intuition behind R is, okay, we can compute P, a false positive rate, given we know N and M ahead of time. So we construct our first layer, let's say at a 5% error with storage for 1,000 items. We run out of space, and now we make a new layer that's 4,000 in size. But now if we target the same false probability error for the second layer, we actually get a compounding error, because the chance that the first layer returns a false positive is 5%, and the chance that the second layer has a false positive is also 5%. So these errors we can't ignore the fact that each layer is actually augmenting the error of the total system. And so what you have to do is actually do a kind of a probability reduction for every level. So every new level you add, you have to tighten that p-value a little bit, because you're basically the end error is kind of the integral of all of their false positive errors. And so it's not very intuitive what this R value does to the system, but if you specify a very small R value, so basically you're saying, tighten the probability of each new layer by only 5%, well then each new layer has to be vastly larger to compensate for it, right? So instead of adding 4 times as many bits into the next layer, it's like, oh, okay, well, my original false positive error rate was 5%. Now you want me to be only 5.05%. Okay, to do that, I have to be, 100 times bigger than the next layer. So your storage growth is very large. If you go the other way and you really ratchet down the false positive rate with every new layer, then basically the initial layer, the smallest first layer, has to be enormous, basically. So, if your target P was 5% and you set R to something, huge like 0.99, then, layer 0 has to be 100 times bigger than you might expect it to be. So there's kind of this weird trade-off there. And again, the paper kind of unpacks this a little bit and says, well, if it's slow growing, set it closer to 0.08 or 0.8. If it's large growing, set it closer to 0.9. And it kind of, you can graph out what the effect is of setting this R, but it follows this log curve. So the sweet spot really is between 0.8 and 0.9, and then it quickly dives to 0 for, very small growth rates, and it asymptotically approaches 1 for insane growth rates. So you just pick a number in that range. And so kind of what are these scaling Bloom filters like in practice? So in our initial analysis, we said, okay, well, if we had 1 million filters and each one only needed 1.6 megabytes using a standard Bloom filter, well, we knew we would only need 1.6 terabytes. But the problem is there's a very large variation in cardinality between estimating how many monthly unique users Angry Birds has in the United States versus the daily Mexican users of Flashlight Magic, right? Like, one might be on the order of tens of millions, the other might be like 5. So it's, you don't really want to set them to both be a size 10 million Bloom filter, right? It's an enormous waste of space. So, within the agency I worked for, what we do is instead pick a, conservative initial N, something like 32,000, and then the layering up, if you're multiplying by 4 each time, quickly we'll ratchet up to like 8 million for something very large like Angry Birds, but you still only need like 5 layers. But your initial layer ends up being 256 times smaller than if you had just started at the largest possible size. And so in practice, where you would estimate we need 1.6 terabytes of RAM, we actually only needed 11 gigabytes of RAM. So now instead of a cluster of, many very beefy machines, we can fit it on one machine actually very comfortably. And that's a very cool result. So as a quick aside, this paper wasn't mentioned, but I would feel bad leaving it out. There's another extension to Bloom filters called counting Bloom filters, and they let you support the delete operation. And so the idea behind this is instead of just storing a 0, 1 at each index, we actually turn it into a saturating counter. So, if we have a 2-bit counter, we can count up to 3 elements per index, 3-bit, 7, so on and so forth. Won't get into the details there, but basically what you're doing now is when you add an item, you increment the counters at all the indexes, and contains just checks is everything over 0, basically. And delete is, the inverse, you just subtract from all of them. Where this gets complicated, and there's some nuance, is, okay, what happens when you saturate the counter in either direction? And so that's an interesting case. So this paper is also interesting if you're interested in Bloom filters and like what is the field of research around them. Take a look at counting Bloom filters. They're kind of cool. So what's the like TLDR on this thing? Like we've talked about a lot of things. Like what should I take away from this? Bloom filters are effectively sets with allowable error. So they let you specify, your hash set has a p-value of 0. It will never return a false positive, but it requires an immense amount of storage, right? The Bloom filter, the moment you turn your p-value slightly over 0, you get an enormous 100,000x or 100 or 1,000x reduction in your storage, depending on your settings. And so it allows you to trade this false positive rate for space utilization in a really elegant, very simple to understand way. It's also a very rich field of research. It's been around for a long time, so you can just deep dive into it. There's a lot of, it starts getting to be diminishing returns on some of the optimizations, but it's still interesting. And then the system we used at the ad agency is open source under my GitHub. If you're interested, you can kind of go poke with it. So now let's transition hard stop to HyperLogLogs. Actually, we'll take a quick moment. Does anyone have a burning question about Bloom filters that they would feel unsatisfied if it wasn't answered? Okay, cool. We're just going to plow forward. So HyperLogLogs. So before we kind of explain the algorithm itself, let's revisit kind of the ad network problem space. So the biggest problem was really this cardinality of figuring out for an interval, country, and app, how many uniques were there in that combination. And so we had this explosion, we have 1 million combinations, but if you paid very careful attention, you'll notice that what we did is we called add and we called size, but we never actually called contains, because we don't actually care if any particular user is a member of that set. Really what we cared about at the end of the day was how many Angry Birds players were in the US, right? We didn't care if a specific person was. So what if we sacrifice the ability to check for any particular item? Can we still get the add and size to do what we want? So it's not quite a set anymore. So let's talk about a hash function, right? One way to think about it is it's a transform where you give it an item, and it's going to give you a bit stream back. So you're just going to get a sequence of ones and zeros, 32-bit hash function, you're going to get 32, 64, so on, whatever. But basically, think about it not as like, I'm going to get an integer back, but I'm going to get a stream of bits back. And a good hash function distributes its values uniformly. And so when we say that, what does that really mean? What we mean is that the value of each bit should be independent of every other bit. So if bit 0, if the first bit is a 0, it should say nothing to us about what the value of the next bit is going to be. And so, so given we have this hash function, and it's giving us this bit stream back, and we know that all the bits are independent of each other, well, what's the odd that the first bit is 0? Well, it's just 1 and 2, right? We have 2 choices. And the odd that the nth bit is also a 0 is also 1 and 2, because they're independent of each other. There's no relationship there. So then if we draw on basic probability, well, what's the odds that we get 4 consecutive zeros? Well, it's 1 over 2 to the 4th. Okay, well, if we generalize that now to n zeros, well, the odd is 1 over 2 to the n, or 2 to the minus n. Again, the assumption this makes is this requires that values are independent. Like, I have to nail that in, because otherwise you'll try and apply it somewhere that it shouldn't be. Okay, so let's play a guessing game. So now that we know that, the probability of n consecutive bits being a certain value is 1 over 2 to the n, how many samples then are required on average to reach n? So if I tell you I witnessed 32 zeros in a row, right? If you had to guess how many inputs I'd sampled before seeing that, you'd say, well, the odds of you seeing that were 1 over 4 billion. So probabilistically speaking, you probably saw 4 billion samples, and one of them had 32 zeros in the leading zeros. Okay, so I've told you that I've seen 32 zeros in a row, but how much space does it take for me to store that fact? Well, if you just break it down into what it would be represented at in its binary format, it's actually just setting the 6th bit to a 1. So I actually only need 6 bits to remember the fact that I've seen 4 billion items, right? And so we can actually count into the 64-bit space of items with only 6 bits. And so hence, this is where the log naming scheme comes from, right? The log of 2 to the 64 is 6. And so we've now kind of gotten why it's called log. We're not quite at the hyper part of it yet. But the really cool bit, and this takes a while to set in, is just like the absolute disparity between how much storage we're using and how many distinct items we're able to count is just kind of amazing. It blows my mind still. Unfortunately, we have these bad apples. So it might just happen to be the case that the first time we hash foo, we see 32 zeros in a row. And so now I'm going to say, well, I probably saw 4 billion items, even though I saw 1, right? And so there's kind of this extreme sensitivity to these outliers, right? In this case, we're off by, 4 billion, which is a pretty bad estimate. And so, okay, one answer might be, well, what if we do multiple samples, right? Like maybe we do multiple hash functions, or, somehow we have multiple of these registers such that if one register is completely blown away and is guessing it's in the billions, maybe the other one is more sane and is going to say 1, right? So can we go to a multi-register model? Well, one way to do this is actually to say, well, we already have this convenient bit stream, and realistically, we don't need all of the bits in the stream. So what if we made m registers, which were a power of 2, and that's really just for convenience here. And what we'll take is the first few digits of this hash function, and we'll have that be an offset into our register table. So instead of now remembering 1 number, we're going to remember m numbers. And so we take the hash, we partition it into an index as well as the 0 count. And so now what we're going to remember is, okay, in our first register, we've seen 2 zeros in a row, right? And so now we tweak this a little bit. So now what our add function does is it takes the hash, it computes the index and the number of zeros, and then we update the offset in our registers table and just set it to the maximum number of zeros we've seen. So it's a slight modification here. But now we have this different question of, well, how do we compute size now, right? So we went from 1 register where it was really obvious. We just raised 2 to whatever power we had. But now we have m different registers, and they all have a different value in them. So given that we have this set of registers, we need some kind of a reduction function, right? Like I have m numbers, I need to get one number back. So you could think that there's like a number of different reduction functions you might possibly use. You might use min and just say, hey, what's the lowest number the system estimates? Or max, what's the highest? What's the average? What's the median, right? There's a bunch of reductive numbers that can take in a sample and give you a single number back. Now, it might be obvious that min and max should probably not be used because if you're sensitive to outliers, now you're going to be even more sensitive to outliers. So we'll just throw those out immediately. Because, yeah, so like the key here is that we're sensitive to outliers. So whatever reduction function we're using has to reduce our sensitivity and not increase it, right? So the original LogLog paper proposes a geometric mean. So it's the, again, this is really fancy math equation software here. It is the nth root, basically, of multiplying all of the samples within the distribution. And the effect it has is also to kind of reduce the effect of the outliers in the system. And what HyperLogLog proposes is don't use geometric mean, use the lesser known of the means, which is the harmonic mean. And the harmonic mean, again, very sorry about this formatting, I wish I had more time, is effectively it might be hard to imagine what this formula actually looks like, but if you basically take, like, let's say the numbers are 1, 2, and 3, it's 1 over 1, 1 over 2, 1 over 3. You add all of those together, and then it's all of that is inverted and multiplied by n. But basically, there's, you know, the main purpose of doing the harmonic mean is that it's the least sensitive to the outliers, basically. So there's a few different means we might talk about. We might talk about the arithmetic mean, which is the very simple, when you think average, that's what average is. Then there's geometric mean, harmonic mean, and root mean squared. And so all of them, depending on like your A and B value, generate a slightly different one. So you can kind of see why arithmetic mean starts being bad, right? Like if A is our outlier here, and it's way overestimating, well, these two are tending to skew us towards this much larger number, which is what we want to avoid. And so the geometric and harmonic mean both tend to skew more this way and avoid going big due to these huge estimates. And so now our size function is changed a little bit. So now what we do is we first take the harmonic mean of all of our registers, and then we estimate, basically multiply our harmonic mean times the number of registers we have, times this A value, this bias correction value. So the reason we multiply the M times HM is because we're taking every sample and we're indexing it into a specific register. And so each register is only saying 1 over M of the input stream. So the expected value of the harmonic mean is actually divided by M. So to correct for the fact that every register is a subsample, there's the multiply by M. But then the question is, okay, well, why is there this A? Where is that A coming from? Well, let's go back to kind of the expectations we had of this hash function. So we have a hash function. It's giving us these streams of zeros and ones back. And we're saying with some probability, 1 over 2 to the n, we're going to see n consecutive zeros. But then you might say, well, what was the probability distribution of this? And this is where the math starts getting really hairy in the HyperLogLog paper, probably around page 4 when everyone's like, oh my god, there's way too many equations here. But the kind of more intuitive way of thinking about it is, well, we expect with n equals 8 samples that we'd see 3 zeros, right? But there's some distribution of other possibilities, right? It might be the case that we actually see, 8 zeros in a row or 9 zeros in a row. It's incredibly unlikely, given that we have a good hash function, but it's still possible, right? And so, yes, that's our expected result, that's our mean, but there is this distribution, there's this tail that we have to worry about here. And so there is this kind of extra zeros with some possibility. So if your eyes were also glazing over, don't worry, I only probably retained 1% of what that section was talking about as well. But effectively, they're unpacking this and doing a Poisson analysis to say, like, okay, well, what is the effect of this tail, basically? How is this screwing with our assumptions? And so what they find, if you kind of grind through all of the math in there, is that, well, as we increase the number of registers, that we're reducing the bias, basically, right? I don't know if there's necessarily a strong intuitive way of explaining that, but it's just like each particular bucket becomes less likely to get hit with that one sample that's going to say, oh, all of a sudden there's 5 billion inputs, right? And so we're kind of the overall estimate of if you're harmonic meaning all of them, basically, because instead of, if you have 4 registers and one of them gets slammed, right, then effectively, 25% of your inputs are really bad. If I have 1,000 registers and one of them gets slammed, it's only affecting 1 in 1,000 of my inputs to the harmonic mean. So this bias factor, as you increase M, approaches 1. It asymptotically approaches something like 0.734 or something like that. And because you're multiplying this by the harmonic mean, its effect is we're reducing the estimate of items, right? So that tail has basically the tail effect of that Poisson has the effect of causing us to overestimate. And so this A factor is reducing our estimate and bringing us closer to what we actually expect it to be. So we kind of are, if you're looking at this, we're kind of guarded by that undercount situation of being to the left of our expected value because we're using the max function. So when we're setting each register as value, we're setting it to the maximum number of zeros of this sample's number of zeros as well as every other one, right? And so if you get if I saw 3 zeros and the next sample says, oh, there's 0 zeros in a row, well, the max of 0 and 3 is still 3, so the tail doesn't affect us or the head of it doesn't affect us too badly. The overcount is then mitigated by this bias correction factor. Okay, so now let's go back to the harmonic mean. It has this nasty little gotcha in there, which is that part of computing it is that we have to take the inverse of the sample. Now, the problem is that if our sample happens to be 0, the value isn't defined. So we can't actually take the harmonic mean if one of our buckets happens to have a 0 in it, right? And so what we have to do, and so I guess, the intuition behind, okay, if we're dividing our stream equally between these 1,000 buckets, and we have a bucket that has a 0 value, then what this means is we must have sampled very little data, right? Because if we sampled 1,000 items, there should be some value in at least all of them. And especially as you're starting to go to n is way larger than m, the probability that you've got 0 in there is rapidly approaching 0. And so what this means is that we must have a very small sample size. And so what the paper proposes is this alternative approach, which is what they call a small range correction, which is as you're kind of starting to compute the harmonic mean, you count the number of registers that have a 0 value in them, assign that to V, and then if V is basically non-zero, so some of your registers don't have a value, then you change your estimate from using harmonic mean into this value, which they also don't really talk about that much, but if you kind of play with it a little bit, you'll get a little more of an intuition. So for example, if you mentally map out okay, let's set V equal to, M, every single index is 0, then log of M over M is 1, log of 1 is 0, the estimate is 0. We expect that there's no items, right? That kind of makes sense. And so you use the small range correction as long as your sample size is very small. Then you have the kind of opposite side of this problem, which is, okay, we've set each of our registers to 5 bits or 6 bits wide, and we're using a 32-bit hash function. Well, what happens is as our samples start approaching the full domain of this hash function, as we start having 4 billion different inputs, we're going to get an extreme amount of hash collisions, right? Because there's only so many bits that the hash function can generate. So as we start approaching the full domain size, the collision rate will increase. And so what's going to start happening is we're going to tend to underestimate at that point. And so there's basically a large range correction they mention, which is, okay, as we start getting very close to the saturation point of these things, you have to start over-multiplying instead of under-multiplying to correct. And what we'll see in just a minute is that it's actually pretty much irrelevant these days because you just move to a 64-bit hash function and you add 1 extra bit, and then it's impossible for the situation to happen. Okay, so we've done all of this math, and we've now spent way too much time thinking about Poisson, and what was the net result of all of this? Well, now the paper has proven for us that if we follow this approach, we can actually bound our error to only 1.04 divided by the square root of m. So we have this tunable here, which is, okay, given that we have some target error, we can play with it and compute what our target m should be. And so in a very, just to provide some examples, if we want to have our, if m is set to 512 buckets, and each bucket is only 5 bits wide, then we'll have a 4.5% error, but we'll only need 320 bytes to be able to count distinctly into the billions.
And then if we say, no, that's a way unacceptable error, and memory is cheap, why are we even talking about 320 bytes? Maybe you set your M to 4,000, you move to a 6-bit counter, and we drop our error all the way down to 1.6%, and now we're still using less than 1 page of memory. And so it's like, there maybe isn't as much shock and awe as I would have expected, but I find this to be outrageous, right? Like, we're not even using a single page of memory, and we're able to count distinctly with less than 2% error into the trillions. Like, it's not even a page of memory. Like, you can't even start Python at less than 10 meg. Like, this is insane. So the question is, can we do even better than this, even though it's already insane? And thanks to the kind folks at Google, we have HyperLogLog++. So they've taken HyperLogLog, and now HyperLogLog in practice is the algorithmic engineering and pushing it to the state of the art. So they basically propose 3 different enhancements. One is moving it to a 64-bit hash and a 6-bit register. One is a bias adjustment, and one is a sparse representation. So we'll talk about all 3 quickly. The 64-bit hash one is the easiest to explain, which is that whole large range correction that HyperLog had was a result of the fact that it was using a 32-bit hash function. And so as you get close to that, as you're in the 1 billion, 2 billion, 3, 4 billion range, you're kind of saturating its ability to generate leading zeros. And so you start generating all these other kinds of errors. But if we just add 1 extra bit and move to a 64-bit hash function, well, now then to saturate the counter, you really need 2 to the 60 items, at which point, like, the heat death of the universe is your limiting factor and no longer your, like, large range correction anymore. So it just makes sense for almost all practical purposes. If you think you might even have a large cardinality, you just go to 6 bits. You don't even implement the large range correction. Problem goes away. And as the paper talks about, even if we get to some world where, like, 2 to the 60 entries start seeming reasonable, then you add a 7th bit and go to a 128-bit hash function, and once again kick that thing down the road for, many decades. The next contribution they make is, well, HLL proves that our error is bounded by this 1.04 factor, but it's not uniform that anywhere in those cardinalities we're getting that bounded error. There's parts of the spectrum where our error is actually much higher and parts of the spectrum where our error is much lower. And so can we do better and basically maybe not change the error bound, but reduce the error along the entire spectrum? And so what they do is they do an empirical analysis of this. And so what they do is they basically, I think is 5,000 different data sets they generate. And so, they know the absolute cardinality, right? Like, I guess they've invented MapReduce, so they can figure that out. But they know the absolute cardinality, and then they run it through HyperLogLog and compare the two. And they can basically figure out, okay, HyperLogLog said the raw estimate was 65,000 whatever, the true value was 66,000 whatever. That bias correction value was off by a little bit. So we can compute that bias correction and then compute the corrected bias correction based on knowing the real number, and then basically shove that in a lookup table is really what they're doing. So you take all of these empirically calculated corrections, put that in a lookup table, and then do an interpolation. So at runtime, you do the same math that we talked about with the harmonic mean and the original bias correction. Then you do a binary search in this correction table, and it says, oh, okay, well, Google knows best. They know that actually we should multiply by this other number, and now we've reduced our error across the whole spectrum. The last contribution, I don't find it to be super particularly interesting, is basically a sparse representation. So, one problem you might imagine is, let's say I have 16,000 registers, but I'm estimating a very small cardinality. It might be the case that all of them are 0, right? Like if the cardinality is 5, right, then probably 16,000 of my registers are 0. So I've stored all of these zeros unnecessarily. And so the first kind of approach to solving this is, well, instead of storing a fully materialized array, why don't we just store a list, which is like the bucket number and its current count? You're like, okay, cool. And now we just scan through a sorted list and update that thing. And it's like, if it's missing, then you just insert it into the list. And so with that, it's something like 25% reduction, or something like 25% of your indexes can be 0 before you need to fully materialize. And then they add a few other interesting techniques. So one is a variable length encoding. So instead of every single index being 5 bits wide, you might get clever and figure out how to maybe store a 0 in 2 bits instead of 5 or 6, right? And then the final one is a difference encoding, which is, I have 16,000 registers. What I could do is say, okay, index register 0 has 2 items in it, and register the next register has 3. And so instead of storing 2 and 3, I'll store the delta. So I'll store 2 and the delta is 1, and maybe the next one's delta is 0. And I can store this delta number as a smaller value. But as you can start, like, you're kind of getting the intuition that you're like, well, like, what are we actually really saving here? We're like variable length encoding 6 bits down to 2. Like, is it really even worth it? Like, why bother? So, you know, they add a lot of extra complexity to do this kind of sparse encoding, and it's a trading of time for memory. So it might be that in Google's very particular use case, they have a lot more time than they have memory. And all of this optimization only even helps you in the sparse case. If your data is not sparse, you end up having to materialize the full array anyway, and there's no memory saving. You just have a bunch of algorithmic complexity. And so HyperLogLogs in practice, let's kind of go back again to like the add problem space. So we have this giant cardinality of like 1 million. And when we first started, we're like, okay, our hash table requires like 750 terabytes of RAM. We were able to get that to like 11 gigabytes with scalable Bloom filters. And so in practice, what we were able to do with HyperLogLog was actually get that down to 4 gigabytes. And the biggest limitation there was our implementation used basically a single page per entry, and because each thing was page aligned. And so really most of the cost was actually still just internal fragmentation. I think probably closer would be 2 gigabytes realistically. And on the very edge case that you're pushing millions of updates per second, the scalable Bloom filter, you might have to run something like 10 hash functions because you have 5 layers. Each of them has 2 hash functions. HyperLogLog, you only ever have a single hash function, right? So you're saving at least like 10x also on your compute time of running all these hash functions. And so again, TLDR, what is the takeaway? When should I use these? They're cardinality estimators with tunable error. So what they give you is a lot weaker than a set, right? There's only very specific problem domains where you strictly care about cardinality. And these are great for those particular problem domains. And they allow you to trade error for space utilization, which is kind of the theme of this. This system is also available on GitHub, which is the one we were using in production. And so stepping back and kind of looking at the broader field, all of these algorithms fall into kind of a family of sketching data structures. And what they let you do is trade exactness for either time or space. Usually both, and then within their particular implementation, there's even more subtle trade-offs between time and space. But on the whole, you're gaining a much faster implementation, a much lighter implementation, but you're losing your exactness properties. And they're very interesting in the large-scale data processing or streaming processing situations where most of these algorithms are designed to be done online. You don't have to do like a giant batch MapReduce job to figure them out. And I would highly, highly recommend looking at the work of Muthu if you're interested in this field at all. It's kind of a very niche field, and he's invented like most of it. So if you just go through his publications, it's kind of the full chronology of everything in this field, with a few exceptions. And that's it. Thanks a lot, guys. So I think we have some time. I'm happy to answer some questions. Let's see. I think there's a spare mic here. I don't know. I'm going to turn it on.
Test. One thing that's worth mentioning is that the sketches also admit intersection and union operations. So you can independently sum up subcategories and then roll them up to the top without having to do a separate sketch or a separate HyperLogLog.
Yeah, that's true. Yeah, both of them, both Bloom filters and HyperLogLogs allow you to do kind of some of these more fancy set operations. Where things start getting weird is the error calculation as to like what those start doing gets a little strange, especially depending on what operations you're doing. So if you wanted very rough estimates, there's some cases where some of the operations are very well defined what they'll do to your error. Some of them are quantified, but the error explosion can be really high. So it just depends on your use case. But yes, there's a really interesting field of like, okay, now I have these Bloom filters. How do I do a union or intersection of them? That's kind of cool. But yeah.
I missed on Bloom filters how a Bloom filter estimates the cardinality.
Oh, you just store a counter on the side of it, basically. So when you do an add, you do a contains first. If it contains, you no op it. Otherwise, you just increment the counter.
It wasn't very clear to me in the Google paper, HyperLog++. That whole thing where they know the cardinality already to adjust for the bias of the data structure that helps them get the cardinality. Like,
yeah, okay. So the way they do it basically is, okay, you know ahead of time, basically, they have a known input, which is like, we know our cardinality of this data set is like n, basically. So let's take that and then run it through the HyperLog algorithm and then kind of remember what all of these sub-estimates were. So like, what was the harmonic mean it calculated? What was the value of all of its registers? And figure out kind of the guts of the cardinality estimation, what those values were. And then record all of those for all of these runs, basically. And so then what they computed was I think they said that, they basically plotted all of these things and then did like a k-means cluster. So they did a few different levels of regression, but to figure out, okay, on these 5,000 different data sets, at the particular cardinality of, let's say, of 20,000, that, one was off by this much, the other was off by this much, let's do like a k-means cluster and figure out like, what did they all tend to be off by? And so there's a kind of a common, across all of those data sets, what multiplier basically would reduce all of their error, basically. And so they calculate that value, which is, okay, if we had multiplied the estimates of all of these results, what would generate the lowest error expectation? And that number basically gets put into a look-aside table. And so then what you're doing is, when you actually run contains, you figure out that raw estimate, just like they did, and you do a lookup into this table. Say like, okay, we know our cardinality is 50,000. When Google ran this, among the 5,000 data sets, they figured out the best corrective factor was this other thing. So that's kind of how they do it. Does that clarify a little bit? It's a few levels of like indirection.
Good question. You implemented this in code, right? So how do you write tests for this, given that the answers are a little bit inexact?
Yeah, testing is really interesting. So what we did was we kind of similarly to Google generate these giant random data sets where we know the value ahead of time. So we did a few different versions. One was basically generate a lot of just random UUIDs and then run that through the system and then verify, okay, was its false positive rate or the error rate within the bounds it should have been? And then the other was real world data. So we have that whole stream as well as a batch processing system. So run it through the system, figure out what its error estimate was based on just running the data through, then do an offline batch computation that's exact, then compare it with real world data. So we kind of did a similar approach. We didn't have 5,000 data sets, but we had a few random data sets as well as a few empirical data sets. And that was basically our approach. The question was, are any of these algorithms used for HashiCorp products? These two are not, no. There is a different one by the Muthu guy called something called like effective computation of quantiles. And it's an approximate method of computing things like 95th and 99th percentile without storing the exact values and basically sorting them. And that's implemented in kind of our StatsD implementation called StatSite. We use that behind a lot of our products. Cool, awesome. I don't think there's any other questions. Thank you, guys.